We're continuing with Chapter 7 on techniques of integration. In this video, we're going to go through section 7.2, which discusses trigonometric integrals. And so trigonometric integrals is just referring to integrals involving trig functions, specifically only trig functions. So not mixtures of trig functions with other functions. So it says, in this section, we use trigonometric identities to integrate certain combinations of trigonometric functions. We start with powers of sine and cosine. Okay, so we're going to look at integrals with powers of just cosine, powers of just sine, or mixtures of powers of sine multiplied by powers of cosine. So here, how do we integrate cosine x cubed? And so the idea is, if we can separate this into cosine squared of x times cosine x dx, then we can use this identity here, sine squared x plus cosine squared x is equal to 1, to convert the cosine squared into 1 minus sine squared. And so this cosine cubed x, you can convert that into 1 minus sine squared x times cosine x. And what that allows you to do is you can use the substitution that u is equal to sine x, and therefore du is equal to cosine x dx. If you put it in this form, it allows you to make a substitution that's going to work. So by saying u is equal to sine x, du is equal to cosine x dx, you can convert the integral into this integral, 1 minus u squared du. You can solve that, then substitute back the u back for sine of x, and you solve the integral. And so with that, you can think about how you could have any odd power of cosine and then solve it this way. Cosine to the 5th, cosine to the 7th. And then what you could also think about is you could do the exact same thing with any odd power of sine, except the substitution in the end would be u is equal to cosine x. So it says, in general, we try to write an integrand involving powers of sine and cosine in a form where we have only one sine factor and the remainder of the expressions in terms of cosine, or only one cosine factor and the remaining of the expressions in terms of sine. Yeah, that's the idea. Because you want to substitute for sine or cosine, and then the resulting du is equal to like sine x dx or cosine x dx. So you're trying to separate the integrand into like something cosine x dx or something sine x dx. Well, okay, it actually would be, you want to separate the integrand into some function of just sine and then cosine x dx, or some function of just cosine and then sine x dx. And that allows the substitution to work. And what you can see is that if you have just an odd power of cosine or an odd power of sine, you can do that. Okay, so that's one method you can put in your toolbox if you come across an odd power of cosine or sine, just cosine or sine. No, we're not multiplying cosines and sines yet. So just an odd power of sine or odd power of cosine. We just talked about how you solve that. Okay. Now, what about we have a power of sine multiplying a power of cosine. To solve this, we're going to use the same strategy where we're trying to separate this into, like I just say, function of sine cosine x dx, or a function of cosine sine x dx. So how are we going to do that here? It says we could convert cosine squared to 1 minus sine squared, but then we have an expression in terms of sine x with no extra cosine factor that would allow us to do the substitution. So what they're going to do is you come to the odd power here of sine, you take out a sine x dx, or just take out a sine x, so you have a sine x dx. Then with that, you want to convert the remaining expression to just cosine. Since you have a sine x dx, if you convert the remaining expression to just a function of cosine, then you can substitute u is equal to cosine x, and you get a sine x dx factor. So that's what they do. So they take out the sine x here, and then you're left with sine squared x squared, and you could convert sine squared x to 1 minus cosine squared x, and there you go. Now you can substitute u is equal to cosine x, and you get this, 1 minus u squared squared times u squared, and then there's a minus sign that comes out of the differentiation, but this is what you end up getting as a function of u. We can solve that integral, substitute back u is equal to cosine x, and you solve the integral. Okay, so now here, what you can see is you can generalize what we just did to where, okay, so you're multiplying powers of sine and cosine. You need one of those powers to be odd and the other to be even for this to work. Because like you can, what we just talked about, we could have easily done the same thing if we had an odd power of cosine and an even power of sine. However, if you had both were odd powers or both were even powers, we have to come up with another strategy to solve that. You're multiplying some powers of sine and cosine. If one of those powers is odd, the other is even. Whether it be the sine is odd, the cosine power is even, or the cosine power is odd, sine power is even, you could solve that with this method. All right, so an odd power of just a sine or cosine, or a product of powers of sine and cosine where one is odd, the other is even, we can solve. Okay, now next they talk about how would we approach if we're multiplying powers of sine and cosine, but both are even. Not both are odd, but both are even. In that case, we can use these identities. Okay, now this actually includes if, so here we're not multiplying, we don't have a cosine. I guess you could say the cosine power is 0, but it's just an even power of sine, right? We never talked about how to solve even powers. It was just odd powers here of just a cosine or sine, right? So we would use, for this case, we can use this identity, these identities. So this is, if you just have a sine or just have a cosine power and it's an even power, we use these identities to solve it. If you're actually multiplying two powers of a power of sine and cosine and both those powers are even, we can solve that using these identities. And you can see, so here what they do is, this is the case where, you know, like these, they call them double angle identities. In most problems, when you have like a cosine of 2x or a sine of 2x, to solve the problem, you want to get out of that, right? In a lot of cases, you're trying to separate the trig function into, you want to get rid of that like 2x or that 4x or that factor. Well, for evaluating integrals, it's actually, in a lot of cases, it's more desirable to have this because you can integrate this, cosine of 2x, right? So we go in the direction where we want to get this cosine of 2x. And now this is no problem to integrate. This is hard to integrate. This is easy to integrate. Separate it into two separate integrals, and there you go. Okay, here's sine of the fourth dx, and they just use that same formula. 1 minus cosine 2x over 2 squared. You could separate this into two separate integrals, and it's easy. Okay, so now they give a summary of the tools we now have in our toolbox. These are trigonometric integrals that they only contain trig functions. And all we've learned so far is integrals that contain just sine, just some power of sine, just some power of cosine, or some product of powers of sine and cosine, okay? But we've only learned specific cases where actually, if you have just a power of sine or just a power of cosine, we can solve all of those cases. If it's an odd power of sine or cosine, then you take out one of those factors and use sine squared x plus cosine squared x is equal to 1 to separate the remaining function into sine or cosine, and then use the u substitution. If it's an even power of sine or cosine, we use that double angle formula. Now, if you're multiplying powers of sine or cosine, we talked about how to solve if you have the case where one of those powers is odd and the other is even. And it doesn't matter which, and it could be either or. The sine power could be odd, cosine even, cosine power odd, sine even. But that's it, though. We didn't talk about cases where you're multiplying powers of sine and cosine and both are even or both are odd. But we'll talk about that in a little bit. All right. We can use a similar strategy to evaluate integrals of the form. So tangent to some power of x and times secant to some power of x. This is similar to what we just did. Not exactly the same, but it's a similar idea. So why is it not exactly the same? Well, because the derivative of tangent x is not secant x, or like minus secant x. It's secant squared x. So you see that's a little bit different than sines and cosines. And then the derivative of secant x is secant x tangent x. It's not like tangent x or minus tangent x. So it is a little bit different. But the idea is the same in that if you have, so here we've got an even power of tangent and an even power of secant being multiplied together. And we can solve this. We didn't talk about a way for solving this case for sine and cosine. But here, what we can do is we can separate a secant squared x, and then so we're left with tangent to the 6th power of x, secant squared times secant squared x, and then secant squared x dx. Then, so we're going to be using this formula here. We use sine squared x plus cosine squared x is equal to 1 for sine x, cosine x powers. But here we're going to be using secant squared x. It's secant squared x minus tangent squared x is equal to 1. Secant squared x is equal to 1 plus tangent squared x. We're going to use that to make this a function of just tangent x. That's the idea. One way of looking at this is we want to, if we have a product of powers of tangent x and secant x, we want to separate out a secant squared x dx and then convert the remaining function to just a function of tangent x, which allows us to then say that u is equal, make the u substitution that u is equal to tangent x. Therefore, du is equal to secant squared x dx. And you can see that you can only do this if you have an even power of tangent x multiplying an even power of secant x. Because you're going to separate out, well, actually, I take that back. It's really, you just need an even power of secant x to do this. The power of tangent doesn't have to be even. It can be anything. Why is that? Because you're going to take out a secant squared x dx, and then you need to be left with an even power of secant x, or left with nothing else. Like if this was just tangent to the 6 of x, secant squared x dx, then you could just start by making the u substitution u is equal to tangent x, no matter what the power of tangent x is, odd or even. But if you have like an even power of secant x that's like greater than 2, then you're going to take out a secant squared x, and you'll be left with an even power, which you need to be left with that even power to convert it, to use this formula to convert it to just tangent x. And then from there you can make the u substitution. Okay? So we just learned when it comes to powers multiplying tangent and secant, or multiplying powers of tangent and secant, how we can solve any case where we've got any power of tangent multiplying an even power of secant. Now, this even power of secant doesn't include secant to the 0. Okay, right? Because the idea is we're making the u substitution that u is equal to tangent x. And so we can't have secant to the 0 because we need a secant squared there. All right, now here we've got two odd powers, an odd power of tangent times an odd power of secant. And so here we can use that we're going to be taking out a secant x tangent x, and then making the substitution that u is equal to secant x, or secant theta here. So we separate out a secant squared factor, and we're left with secant to the 5th. Okay, and so, all right, what they're going to do, so what they want to do is, the goal here is you want to separate out a secant theta tangent theta. So you have secant theta tangent theta d theta, and then what you're left with is something you can convert to strictly a function of secant theta. That's the idea. And you're going to do that using this identity. So can we do that here? So you take out a secant theta tangent theta. Now we're left with this. You need, in this case, you need to be left with an even power of tangent for this to work. The secant power you're left with doesn't matter. So because if you need to be left with an even power of tangent so that you can convert that to purely a function of secant. And so in that case, you have a function of secant and then secant theta tangent theta, so that you can say u is equal to secant theta, and then du is equal to secant theta tangent theta d theta. All right, and so this is a little confusing, but when does this work? So this works when you have an odd power of tangent multiplying any power of secant other than 0. Like you need at least one secant. So any power of secant that's greater than or equal to 1. Okay, so here, this method works for if you have an even power of secant, and then any power of tangent other than 0. And then here, this works for an odd power of tangent and any power of secant other than secant to the 0 power. All right, so they summarize here. If the power of secant is even, save a factor secant squared x, and then convert the remaining even secant power to 1 plus tangent squared x. And so you can then substitute that u is equal to tangent x. All right, now the other case, if the power of tangent is odd, and secant can be any power except for, except for 0, save a secant x tangent x, then convert the remaining even power of tangent x to a function of just secant x, and you can substitute then u is equal to secant x. All right, so those are some tools that we can use to evaluate trigonometric integrals. But as you saw, we didn't cover all scenarios of multiplying powers of sine and cosine and powers of tangent and secant. So what if you're multiplying an even power of tangent with an odd power of secant? What if the power of both the sine and the cosine are odd? What about powers of just tangent or just secant? And so it says for other cases, the guidelines are not as clear-cut. We may need to use identities, integration by parts, and occasionally a little ingenuity. So yeah, just remember, integration by parts is a general method. You can use it whenever you want. You can always apply the integration by parts formula. It's always can be applied. There's never a case where you can't apply the integration by parts formula. It's just whenever you apply the formula and you look at the resulting integral that comes out of it, is that integral solvable or not? But you can always apply the formula and see what you get. And so for other cases, if we just take note of the integral of tangent x, which is natural log of the absolute value of secant x plus c, and we also take note of the integral of secant x, which is the natural log of the absolute value of secant x plus tangent x plus c, then if we've got an alternate case that we don't have a general method for solving it, then just take out the trig identities as well as think of the formula for integration by parts and see if you can find a way to solve it. For example, here, let's look at the tangent cubed of x. Okay, so we've got this identity here, tangent squared x is equal to secant squared x minus 1, but that you wouldn't think that would help us, but they write that in here, so they separate this out into tangent x, tangent squared x dx, so you get tangent x, secant squared x minus 1 dx, and so then they separate this into two separate integrals, and actually it does work, because look, what is this? This is the even power of secant, right? So we can solve this, and all we're left with is solving this and just use the formula for the integral of tangent. So you just have to play with it. You just first looking at this, you would think, well, using this identity doesn't seem like it's going to help us much. But if you apply it and simplify, you realize okay, this is one of the integrals we can solve, even power of secant. And then here we just look up the formula for the integral of tangent x. All right, what about secant cubed x? And so let's do this. We've got secant squared x is tangent squared x plus 1, and then we're left with secant x dx. So we've got secant x tangent squared x dx plus secant x dx. But this, unfortunately, isn't going to work because we've got an even power of tangent and an odd power of secant. The methods only work for an even power of secant or an odd power of tangent. So, okay, well, that didn't work. But what they do is they try an integration by parts. They say that u is equal to secant x, dv is equal to secant squared x. And so remember, the strategy for integration by parts is you want to separate the integral. What you identify to be the u and what you identify to be the dv is, in general, you look at like what's the easiest to integrate and differentiate. And we know that secant squared x is easy to integrate because the derivative of tangent x is secant squared x. So make the u secant x, that's easy to differentiate. Make the dv secant squared x. And now when you set up the integration by parts, you get this. And the resulting integral is what? Is an even power of, well, actually, okay, you do get this. And so actually we could have solved this if we would have just substituted in secant squared x minus 1. So actually we could have done it this way. They just want to illustrate another using integration by parts. So that's just a good example to where just because you don't get an integral that follows the template, just make some trig substitutions and see what you get. Because the idea is, like, if you come across something like this, if you make the main substitution, make the main, it's the tangent squared x is equal to secant squared x minus 1, and just rearrange it, because if you make that substitution, you'll probably get some different multiplication of powers, and that will allow you to solve it, right? Because, okay, so they get this secant x times secant squared x minus 1. You can separate this into two separate integrals, and you're going to end up getting, okay, you get something new, an odd power of a secant and just a secant. Well, okay, so this is what we're trying to solve for, but what do you do? With integration by parts, you're always aware of the fact that you might get the original integral. On this side of the equation, you might get the original integral, in which case you just add that to both sides of the equation. Or you could end up getting like secant squared x. Maybe this ends up being secant squared x. Well, the derivative of the integral of secant squared x is tangent x. So you just apply trig substitutions and just rearrange things as much as you can until you wind up with forms that you can solve, right? You wind up with even powers of secant multiplying a tangent, or odd powers of tangent multiplying a secant, and then separated from that is just something you can solve. Or here we can't solve this, but this is the original integral. Okay, and so with that, all we have to do then is get this integral, and we can just look at our tables for this. And there is the integral. All right, now then it mentions if you've got cotangent, powers of cotangent multiplying powers of cosecant, it's the same types of strategies that we've just gone over, with the main identity being this identity. Okay, now what else? We could have situations where we're dealing with sine of 2x, 3x, and cosine of 2x, 3x, etc., or they could be multiplying each other. So here they've got, it could be, here they got sine of mx times cosine of nx. Here, and then here it's sine of mx times sine of nx. Here it's cosine of mx times cosine of nx. Those are the situations. Or maybe that you just have sine of mx by itself, or cosine of nx by itself. Okay, and so the trig identities that you use in these cases are as shown here. And so this just takes practice. You're just going to have to, we're going to have to work a bunch of examples, and just with practice, you'll get a feel for how to solve these kinds of integrals. And so here's an example, the integral of sine 4x times cosine 5x dx. What these identities allow you to do is, this looks more complicated, a minus b, a plus b, but in general, you're going to be able to combine the a and the b. Like this will be sine of something x, cosine of something x. So this ends up being, you separate this into two separate integrals, which is the goal, right? In that case, you can solve it. So you get, this simplifies to 1/2 sine of minus x plus sine of 9x. Well, now we can just separate that into two separate integrals and solve it. All right, so now let's work some example problems.